Hey everyone, this is Subhabani and I am an analog and mixed signal IC layout engineer and I have been working at ESS Technology, Canada, British Columbia. And this is my first lecture for job preparation, especially for analog electronics. And in this lecture, I just cover common source amplifier and some basic circuitry to just warm up your brain and to just prepare yourself for the job interview, because especially in the job interview, especially in your first job, most of the time you may face these types of question, whatever it is in exam or in the interview. So I'm just sharing the basic thing, which basically very vital for your first job. Okay, let's begin. So this is the basic circuit diagram of common source amplifier. Our input has been applied in the gate and the drain is our output. And this is one of the common question that to find gain, input output resistance, and small signal model for any analog. It may be a common source amplifier, common gate, common drain, or maybe a operational amplifier. So most of the time, you may ask in a written exam and interview about this question, draw a small signal model or find input output resistance of several types of circuits. So to solve this problem, first of all, you need to learn how to find gain, input output resistance, and small signal model of a common source amplifier. And based on this understanding, in our future lectures, I will discuss some more complicated circuit also. So let's begin. A MOS is a voltage-dependent current source, and it acts as an amplifier. To act as an amplifier, a MOSFET should be in saturation region. And the small signal model of this simple circuit, it looks like this. Here we can see there is a current GMV in, and this current, you can see there is a source of dependent current source, and this current depends on the gate voltage V in, or we also can say VGS, gate to source voltage. And if you want to find the gain of this circuit, then using a simple KVL, we can find that the gain of a common source amplifier is minus GM into RT. As an analog IC design engineer, you have to memorize this formula because we will solve many complicated circuits based on this simple equation. So it's mandatory for you to remember this formula. So gain of a common source amplifier is minus GM and RT, and RD is nothing but the resistance tied between the drain and the VDD terminal. If I go to the next page, then I can see to find this input and output resistance. It is also crucial to find input and output resistance of circuit. And in this case, please remember there is no current flow through the gate terminal of a MOSFET. Never, there is no current flow through the gate terminal of a MOSFET. Therefore, the input resistance of a MOSFET is infinite. And in this case also, as there is no current flow in its gate terminal, so input resistance of a common source amplifier, we can say ideally it is infinite, or if you want to see what is the practical value, then you can just simply draw this circuit in Cadence or any simulator, and then you should run the DC analysis. From the DC analysis, you can see the VGS voltage as well as its input output resistance, everything you can see from its DC analysis. But ideally, it should be high. So we can assume it may be in mega ohm range. However, let's find out its output resistance. To find output resistance, please remember to find output resistance is very crucial. I repeat, to find output resistance, we must consider there is no input, or you can consider it is a short circuit. So if there is no input in this circuit, so first of all, we should open the input, or we can short circuit the input, then we can find its output resistance. And we know from the Ohm's law, so what Ohm's law? It's V equal to I and R. So to find resistance, we also need a voltage. So we can apply a output voltage, sorry, we can apply an external output voltage in this side. I did not draw there, but we can consider an output voltage in this side. And if there is a current flowing in this branch, so we can see if as there is no V in is zero as the shorted, so there is no GMI in. So the only resistance is RD. So the output resistance of a common source amplifier is RD. It may be changed, but it may be changed and it should be changed. If you want to play with the common source amplifier, if you want to increase its gain and whatever, there are lots of tuning parameter. Uh, I surely discuss about this topic in the next lecture. So, and then we can see how and why we need to tune this RD. But for the time being, now consider that there's a simple resistance and its value is RT, which is our output resistance. So in the next circuit, we can consider that there, instead of resistance, we can consider that there is an active load. We can consider there is an active load. Active load is nothing but a transistor which is in saturation or act as a current source. Okay. However, for this active load, we also need a voltage VV to make this transistor in saturation mode. So if we want to find out the output, the gain of the circuit, as it is a common source amplifier, there is no confusion. So we know the gain of common source amplifier is minus GMRT. So GN mean the transconductance of the input stage. So we only need to find out the output resistance. Now, instead of RT, we can write that the here in this case, the output resistance is RO2. RO2 mean the drain to source resistance, the source to drain resistance of this PMOS, which we can consider as RO2. So here the gain is minus GMRO2. Similarly, however, in every case, I am considering here that there is no channel length modulation. The channel length modulation coefficient lambda equals to 0. And I'm ensuring you that in the interview, in the written exam or in the interview, if you are going to for any interview in Bangladesh or anywhere in the world, if you are going to an interview for your first job, I mean, is your very beginning first job, then they may ask you very simple circuit. They may ask you very simple circuit like this, whatever I draw here, like this similar type of circuit they may ask you. So you need to draw its small signal model. You need to be able to find its gain, output resistance, everything, whatever. Similarly, it is also a common source amplifier. So if we draw a small signal model, I did not draw there, but in the small signal model, you need to remember that without input, any other constant voltage source, we will consider as AC ground. Please remember, it's not ground, it's an AC ground, mean it's virtual ground. it's not actual ground. For example, here VDD, we consider it is an AC ground. So if it is an AC ground, so here we can see from this example, we already know the output resistance of a active load is RO. So here we will find R3 for M3 transistor and R2 for M2 transistor. So if you can see this two resistance in series, right? This two transistor in, excuse me, this two transistor in series. So, okay, let me check. I wrote here this two transistor in parallel. Okay, let me think. Out. Ah, okay. In small signal model, the input will be grounded and there is, sorry, my drawing is not good. So there is no current. This is the drain terminal. And there is two resistance comes. Okay. Yes, in small signal model, these two resistance comes in parallel because this node is already is virtually grounded and this two resistance comes in. I cannot agree. This two resistance parallel or not. I can see this is the gate. There is no current flow there. Hmm. Sorry for that. I'm a little bit confused here. So there is no current. This is the drain terminal. Hmm. Hmm. I'm sorry, guys. Extremely sorry for this delay. Okay. I hope my screen sharing now. Okay. There is a mistake. These two transistors not in parallel. These two transistors should be in series. So there is a correction. These two transistors should be in series. So the output resistance of this circuit is GM1 R2 into R3, the multiplication of this. So there is a mistake. Okay. In small signal model, I also did a mistake. The mistake is that, I'm sorry, so this R2 and R3 will come in series. Yes. This is the drain terminal from drain. Oh no, oh no. This true is in parallel or two, same potential. Three. Why I am confused here are two, same potential three, and this ground. No, no. There is a mistake in this diagram also. Okay. Okay, whatever, let's begin. So fine. So, but this circuit is really crucial. So you have to be able to find out the output resistance of this circuit. Okay. So find out the gain and R out of the following circuit. So this is the homework. So in this case, we can see, I am helping you. In this case, we can see this M1 and M2, these two in parallel right now, okay? In this circuit, these two in parallel. So the output resistance would be the R1 parallel R2 and this and series with R3. Okay, so the R1 parallel with R2 and series with R3. This is the output resistance, and the gain should be minus GM1, the R out whatever we calculate right now. And if we consider about the advantage of cascading, is that it helps us to input the R out, and if we can increase the R out, then it helps us to increase our gain. And as there is no RT, mean there is no active resistance, so there is no temperature dependency. You know, temperature, basically the resistance, it depends on temperature. If temperature change or temperature goes down, the value of a resistance, it may increase or decrease. So in this way, our gain will not be stable. So if we can remove, or if we can replace this resistance with an active source, then we can find that more stable gain. The disadvantage is that uh, the disadvantage of this type of cascading is that it reduces the voltage swing, because let's say if we want to calculate the voltage V out to ground, then we can find that this VDD, there is a VGS drop here, there is an also drop across M2, then we find this voltage V out to ground. So there is an the disadvantage of this circuit, that there is a low voltage swing, but in this case, as this you can see M3 and M2 in series, so it increased the R out. Eventually, it also increased the gain of our system. Whatever. There is also a term which is called intrinsic gain of a transistor, and the intrinsic gain of a transistor is nothing but the maximum gain. For example, if we replace RD with an active current source, then whatever gain we will get from and common source amplifier, this is the whatever, this is the maximum gain of a current source amplifier, simple current source amplifier. And this gain is called intrinsic gain of a common source amplifier. Okay. This is also an important question. Sometimes in interview, they may ask you what is the intrinsic gain of a common source amplifier. The intrinsic gain is whenever we replace this RD with an active current source, at this point, we will get the maximum gain from this common source amplifier. Definitely, there is obviously there is a limitation of W by L, whatever. But this is the intrinsic gain of a common source amplifier. And usually we will represent the common source, sorry, we represent a current source. We obviously, as the gain is minus GM RD, RD mean the drain resistance. So if we replace RD with a current source, sorry, with a, yes, with an active current source, then we need to find the output resistance of this current source. We can assume the output resistance of this current source is RO, simply RO. So the intrinsic gain is nothing but minus GMRO. I think it's clear. And if you practice these circuits, it's really helpful for you. So now proceed with another circuit. This is one of the important configuration of common source amplifier, that is that with diode connected. So same case, if we want to find the gain, we already learned that the gain is minus GM RD, and here RD is, there is no RD, here is an M2, which is diode connected, mean gate and drain terminal are connected. So in this case, we need to find out the gain. So let's do a small signal analysis for this diode connected load. And from the small signal model, we can see it look like this. And if we did a little bit of calculation, you can see there that after a little bit of calculation, we can find that the VDS by ID, which is nothing but resistance, R, it is like this, 1 divided by GM plus 1 by RD. Typically, the value of RD mean the drain to source resistance. Here RD mean the drain to source resistance of M2 is typically high, than compared to this GM. I repeat, a drain to source resistance of a transistor is significant high than its GM, its transconductance. So whenever we did 1 over RD, then it's mean this 1 over RD is too much low compared to GM. So we can avoid 1 by RD for the simplicity. And then we can write that the output resistance of a diode connected load is 1 over GM. And as an analog designer or layout engineer, you have to be remembered that we can consider the output resistance of a diode connected load, whatever it's PMOS or NMOS, it is always 1 over GM. You should remember this point. And here I also assume a mathematical term to just illustrate this issue. For example, we can consider RD. I also already told you RD is mean drain to source resistance. You can assume it may be 100 kilo ohm or it may be 500, 600. It's typically higher. On the other hand, GM is the unit of transconductance is Siemens. It may be 5 millisiemens or 10 millisiemens. Here I consider 16 millisiemens. So whenever we did 1 over RD, you can see as it is kilo, so it will grow in micro range. So 1 over RD is too much smaller compared to GM. Therefore, we omit this term. So please remember, it is 1 over GM. The output resistance of a diode connected load is 1 over GM. Okay, so in this case, the gain is minus GM R out or RD, whatever you said, and here RD or R out is nothing but 1 over GM. So here we can see an interesting issue. That is that the gain is only a ratio of 2 GM. So this is the beauty of the circuit, is that if we replace RD with a diode connected load instead of an active load, so we'll find more stable gain. How? So let's see how we can get the more stable gain. So let's see, the advantage of diode connection is that we don't need any external biasing source. For example, in the previous circuit for the cascoding, you can see that there is an external biasing point for our PMOS or NMOSs to take this transistor in saturation point. But in the diode connection, you can see we don't need any external voltage source to bias our transistor. It biases itself. And you know, there is an important formula of GM there are several formula, three formula of GM mostly used in the design, but here I only mentioned one formula. It is that rotobar twice ID mu and Cux W bar L. So if we just put this formula in our gain equation, here we can see that just this simple equation. But the interesting point is that here the ID1 and ID2 is same. The same current flow through these two transistors. And mu and Cux, it is an constant parameter. You can assume it's a constant parameter for simplicity. It depends on the fab or some other issue, technology dependent parameter. So it also same for these two NMOS. So we can cancel out mu and Cux from top and bottom, as ID1 and ID2 also similar. So we also can cancel out these 2 points. So what left? There is only left row bar, just W by L ratio of two transistors. And in this case, or always for a better design for a particular technology, the channel length may be same. Channel length should be same. If the length of this transistor also same, then it only depends on the width of this two transistor. So therefore, this gain is more stable. There is no temperature dependent like resistance. Resistance is temperature dependent. So there is no temperature dependent term. Therefore, this gain is more stable. Okay. Okay. This is another beautiful version for common source amplifier. It is source degeneration. If you understand this degeneration, so in my next presentation, I will gradually show you some more complex circuit. But go to any complex circuit first, we need to understand this basic circuitry. So now we need to find out the output resistance of this source degeneration. Here I already wrote down all of the calculations, so you may just pause the video and just see the calculation. For simplicity, I will not explain anything here, but I'll just explain one thing, that whenever the source is directly not connected to ground, the source, there may be a resistance, there may be a transistor. Okay, the source is directly not tied to ground, there may be a resistance of transistor. So this types of configuration is called source degeneration. And to find out its output resistance, so you can pause my video and you can see this calculation. And I'm just explaining one little thing for calculation. You also should remember this small circuitry here on the left side, because here the VGS and the current through this RS resistance is depend on the VGS voltage. Okay, just remember this thing. And you already know, for to find out output resistance, we used to consider there is no input signal, mean input is 0. So based on this, using the simple KVL equation, you will find this complex term. You'll find this complex term. But for simplicity, I will show you something that what you should remember. Let's say there's a calculation also. Let's say there's a circuit that you need to find out its gain. Okay, so for first time, it may be weird for you to remember a complicated formula for source degeneration. So I will show you one simple equation here. This equation is really very powerful. You will find the calculation here. If you are interested, you can pause my video and you can see the calculation. But I want to directly jump the output. The output is that the gain of a common source amplifier with source degeneration is that minus RD is, you already know, RD is nothing but the drain resistance divided by 1 over GM plus RS. So it's very simple. Minus RD divided by 1 over GM plus RS. RS is nothing but the resistance between source terminal to ground, and RD is nothing but its drain terminal resistance. So it's very easy, right? And you also can calculate this gain from here. For example, we can, if there is no input, if input is zero here, and if you just consider a voltage here, V out, this V out voltage should be drained to AC ground, mean drain to ground, this voltage. And if there is a current, so you can, from the Ohm's law, just consider this current is going downward. You can see the symbol here, the current is go downward. So it is V out by RT, V out divided by RT. So current ID is V out by RT from Ohm's law, we know that. So if V out by RT current goes downward, if this is positive, so the same current will also go in the left side. You can see here, it is minus V out by RT, the same current, just opposite direction. And as there is V in, now we need to find out this first, that GMV in. So here, GMV in, this current is equal to this current minus V out by RD. The same current, please repeat, the same current is flowing this branch. So minus GM V in, this current is equal to minus V out ID. Sorry, it's RD, minus V out by RD, the same current. So from here, we can find out the V in value. So, and after finding the V in value, if you just simply did the KBL, KBL where? KBL in this loop. I'm showing you KBL in this loop. You can see the VGS terminal here. So in this side, okay, the gate side, in the small signal circuit, you also can see, if we just did KBL in this side to find out, okay, the same current also flowing through the RS, the same current flow GMV in, and the same current is flowing through RS resistance also, which is minus V out by RT, the current. So if we did a KBL in this side, so then we can find out this equation, V in equals to this, and we also know the V in value. So if we just put the V in value and did some mathematics, we'll find this equation, okay? So it may be complicated for you to remember, so but just remember this thing. The gain of a common source amplifier with source degeneration is minus RT divided by 1 over GM plus RS. And you also should remember this term, that what is the output resistance of a common source amplifier with degeneration. The output resistance, sorry, not for the entire amplifier, just for the transistor which is source degenerated, its output resistance itself is R out, RO means its drain to source resistance plus 1 plus GMRS. And for better explanation, you can find any book, for example, Pajit Rajavi books, for more explanation if you want to learn more about this topic. And yeah, that's everything. If you just know this simple equation, then we can easily find out the gain of this circuit, right? Because we can see there is a diode connected source. Sorry, there is a diode connected MOSFET, PMOS, as well as there is an NMOS, which is in common source configuration, and it's degenerated. So it's simple. We know here is RD. Here RD is nothing but 1 over GM2, as we already find the output resistance of a diode connected load. And we also know the gain of a degeneration common source amplifier, which is what. So from this equation, we just need to replace RD with 1 over GM2 minus 1 over GM2. And here it is GM1. From the formula, it is 1 over GM. So GM is nothing but the input GM. So here it is 1 over GM1 plus RS. All right. It's pretty simple, right? It's pretty simple. We can see from here. Okay. Okay. I think that in this stage, you also able to find out the gain and to draw small signal model of this circuit, because I'm telling you with responsibility that uh, it is very common in job interview and job examination. If you go any job exam, you will find similar type of question. If your job is related to analog circuit, it may be analog design engineer, analog layout engineer, whatever. You may expect these types of basic circuits, so you should be able to find out this. Okay, I expect that you also can find out the gain of this. You can see it is degenerated, right? Because as I already told you, here you can see M1 is my input and it is common source configuration. Here, source is not directly connected to ground. It is connected M3 and M4, then it is connected to ground. So here, there is no RS, but instead of RS, there is M3 and M4. So we need to find RS here, right? So here RS what? RS is nothing but the two series resistance of RO2, RO4. You already know, right? What is RO3 and RO4? RO3 is nothing but drain to source resistance of M3, and RO4 is nothing but drain to source resistance of M4, right? So in these two in series in small signal model, and you also know the output resistance of a diode current load, which is 1 over GM. So from the formula itself, we can find out its gain, right? But here is the beauty. If you know these shortcut tips, then it is easy for you to calculate its gain. But if you draw a small signal model, I know, you can draw a small signal model, and you also can find its output resistance gain using some KVL KCLs from small signal model, but it will be more complicated to find out this in small signal model. But if you remember the formula and if you know how to use this formula, then it is super easy for you. Okay. I think there is maybe some page repetition. This is page 11. Okay, yeah, there's page repetition. Okay, so finally, what is the advantage of this source degeneration? It is your homework. You can search online and you may read book to find what is the advantage of source degeneration. But here I just simply telling you that if you do source degeneration, then your circuit is more linear. If circuit is more linear, if anything happen in the output, in the input, let's say input dramatically increase, or if input decrease, so if circuit configured such a way that it will fix immediately, or you can also follow this relationship here. If my Vin increase, so initially my VGS increase. If VGS increase, the ID or the IS, it's same current, right? It will increase. If ID increase or IS increase, the drop will increase, and again VGS will decrease. So you will study book. I think this point, if you are fresher, you cannot catch this point from here. So you can read a book for better understanding, but I am telling you that this circuit is more stable. Okay, just consider any source degeneration circuit. let's say this circuit, if here my input is increased, Vin is increased, the VGS will increase. If VGS increase, my drain current will increase. If you have remembered the Mosfet current equation, then you will find that Mosfet's current equation is proportional to my GS, right? If my GS increase, my current will increase. If my current will increase, then the same current will flow this IRD and RS. So if the current increases mean the drop across this arch resistance will increase. If the drop increase, so gradually my VGS will decrease again and my ID will decrease again. So in this way, I think you got this point. I explained now it clearly. So in this way, this circuit is more stable and it prefer to work in at a certain point for what this circuit may be designed. I hope this point is clear now, and for now it's adequate. And yeah, and one more interesting point for this source degeneration is that you remember for the diode connector node, we see that the gain is just the ratio of to the width of these two transistor, right? The width of these two transistor. It's the ratio of two width. In this case, I know it's really hard to design, but just for a theory that here we can consider that the gain is ratio of true resistance. How? How? You may find it here that you may avoid their 1 by GM term. If we make RS too much larger, if you make RS too much larger or significant compared to 1 over GM, then we can omit this 1 over GM term. And then this gain is just ratio of RD and RS. So what is the beauty? The beauty is that, R is temperature dependent. So both are resistance. So if RD increase, RS also increase. So in this way, it nullifies its effect. If RD decrease, RS also decrease due to the noise or temperature, anything, whatever. Analog circuits are really noise sensitive, however. So this is the beauty of the circuit, and you also find this relationship. I guess I show one more point here. Okay, in this calculation, if you see this calculation, you also find that here gain is just ratio of two resistance. That's for now. I hope you enjoyed this video, and if you understand it clearly, so there is a homework. Uh, I'm really appreciate you that if you comment below of this video and just try to find out the gain of these two transistors. Sorry, these two circuits, the gain, input and output resistance. Obviously, the input resistance is ideally infinite, but I am really interested in its output resistance and its gain. And you can see the right circuit is a more realistic circuit. You can see to diode connected PMOS, source degeneration. Okay, it's a biasing circuit, whatever. So it's really a good practice for you if you are able to find out the output resistance and gain of this circuit. Then it's clear that you understand this lecture carefully and your valuable time is not waste. And if you are not able to find the gain and output resistance of this circuit, then you may need to work on yourself through more, and or you may repeat this video and try to understand the if any point. However, if you have any question or any inquiry, any type of inquiry, you can just comment and I will try to reply you. Or if you have any simulator, you can simulate the circuit and it is also helpful for you, and you can easily understand the theory as well as the practical knowledge. So bye for now. And if you like my video, please share with your friends. And I really appreciate you if you comment below and just answer these two questions. And again, once again, if you have any question, please never hesitate to make a comment. Bye for now.